Session of the first day of the really big breakout sessions. My name's John. This is Mick. We're from a company called Thinknear, and we're going to talk about how we're serving billions of web requests a day, and we're built on Elastic Beanstalk. So what I'm going to talk about today, first we're going to go over some of the resources we've made available, get that out of the way so you don't have to remember a lot of the really key details. You can take the high-level pieces away and then apply that back when you're at work after. Quick intro, who we are, why did we choose Elastic Beanstalk, why are we still using Elastic Beanstalk. We're going to go through our architecture in a fair bit of detail, the big pieces around and how it all fits together, the technology choices we made. And then Mick is going to go through 3 of the particularly interesting areas where we had challenges at scale and talk about how we overcame those. Great. So the resources, we'll just fly through these. So we put a full snapshot of our Beanstalk config available online. Have the URL in a sec. It's got all our files related to how we're using RAID, log rotate, how we're monitoring, Unix tuning, app server tuning. So it's got all the nitty-gritty details that we've gone through. There's just too much there to actually cover in a presentation. And then we've also open sourced one of the key pieces we were missing, which is how do we get lots and lots of logs into S3 in a reliable way, and we couldn't find an existing way open source, so we created one, and we've open sourced that as well. And then, of course, you can always get the slides after the fact. So if you're looking at the slides now, here are the URLs you care about. We've got a blog that we write about what we're doing and announce improvements, so you can check that out for sure. And the goal of this presentation is at the end, you'll see what we've done and what works for us at scale. We are running tens of billions of requests a day. With anything of that size and doing high-frequency requests with low latency constraints, you always have to test it yourself. But this should at least give you a starting point and the major pieces to consider and how we overcame the challenges we encountered that's particular to our situation. So who are we? So Thinknear is a hyper-local mobile advertising platform, and that is a mouthful. What that means is that we are buying ads on mobile devices. So anytime you're using the mobile web, games, you get those lovely banners that you love to click on, the interstitial ads before you get to play your game, whatever it might be, we are a buying platform for those ads. Hyper-local means that we are really focused on location. So we think where you are matters for whether we're going to show you relevant ads. So we don't show you ads for Walmart, we show you ads for the Walmart that's in your city with local specials and it's relevant to you. Quick history, we're a pretty small and young company. So we founded in January of 2011. We were doing a different product, and fall of 2011, we started on the product we're talking about today, which is the advertising platform, and we started with an engineering team of 2. We launched that platform to production in spring of the following year, 2012, with an engineering team of 3. That got traction, and we actually sold that fall as things started to ramp up. So we're now a business unit inside a larger company called Telenav. For the most part, we run independently. Certainly all the IT is still independent. They act more like investors and advisors, and then we share some legal and HR resources on the back end. So we exist in an ecosystem called RTB mobile advertising. And what this means is it's real-time bidding. So in real time, when you're on your phone and there's an opportunity to show a banner, there's a request that goes out to what's called an ad exchange. And they have thousands of apps that are all sending them their advertising opportunities. They pool this, and then they send a fire hose to us and our competitors with, here are all the advertising opportunities available in the US, say. And so we are listening to this fire hose, hundreds of thousands of requests a second, and picking out the ones we want for our advertisers. And we have a large number of advertisers who are using us to buy their mobile ads, and they all have kind of different requirements. They're trying to reach different demographics, people in different parts of the country, and so we just have all this business logic in there to help us target the ones that our advertisers want. So why Elastic Beanstalk? That's, I mean, as a big scale system, I feel like that's the question people want to know. And the reason is, going back to what I was talking about, Elastic Beanstalk really provided a speed to market when we were first launching. I mentioned we had an engineering team of 2, and Beanstalk gave us a really nice pre-configured starting point with all the Amazon services tied together. It also lowers the learning curve for AWS. So when we started, we were not AWS experts. We consider ourselves experts today, but it started with Beanstalk and sort of an overall knowledge of what the services did, and we were able to get something up and running and launched, and then dive deep into the nuances of each service as we went, or as we had challenges we had to overcome. So from a startup's perspective, it was really great to be able to get on board and get running with very low barriers to entry. So what we're running on Beanstalk is our real-time ad bidder and ad server. So in our architecture, we have a number of services. This is the workhorse. This is the one doing the most requests, processing the most volume of data, doing the most computation. It's got the most servers behind it. So this is our key service in our architecture. We're running on Tomcat. I'll talk a little bit more about that later. We're API-based. So we're not serving a website. We don't deal with browsers. We have a JSON-based API contract that we adhere to with our partners. And the nuance of that is you can't cache anything, or not at the client level. We're doing well over 150,000 requests a second. This was our number from a few months ago, so we're easily clearing that now. We're running hundreds of hosts in production, well over 9 billion. Again, this number's a couple months old, and our hosts are spitting off more than 2 terabytes of data every day. And then with auto scaling, we're up and down. So we basically double the fleet and come down at half. And that's driven by usage patterns on mobile. People aren't doing a lot of mobile gaming at 6 a.m. generally, so we cut the fleet right down and scale back up. Why are we still using Beanstalk? A lot of those reasons I just gave you were reasons to start using it with low barriers to entry and getting set up. But here we are, 3 years after we built the product, still using it. And this is going to seem quaint, but the UI is actually really nice. So being able to go in and have a UI that gives you a quick overview of your different services set up, what's running in production, and having metrics and things all tied together is a really nice feature. Managed deployment mechanism. This is something that there are a lot of competing services out there with. There's Chef Puppet. There's 100 ways to deploy your code. They have one, and it's worked for us. Configuration mechanism. Again, there's a lot of ways to get configuration out to production. This is one, and it's worked for us. Aggregated metrics, that's a nice feature of the auto-scaling groups, tying together CPU, latency, all the metrics from a given Elastic Beanstalk environment into the UI, and being able to quickly see things at a glance, and ongoing development and support. So I think the message is that there are a lot of alternatives to the individual pieces, and they brought it together in a package that has one sort of vision behind it, and rather than putting together different open source pieces into a solution, we were able to just take a whole holistic piece and run with it. And that's continued to work for us, and we'll continue using it until it doesn't work for us, which we don't see that happening anytime soon. So let's talk about the architecture. So what did we actually build on Elastic Beanstalk? So backing up to when we started, we had certain requirements and constraints that we had to adhere to with our architecture. I'm going to go through these because they're pretty typical, but I do want to cover them. It had to be scalable. We started very small. We're more than 100x the size of where we were when we started, and we haven't had to make major modifications. So we had that in mind from day one when we picked our technologies. Robust, reliable, fault tolerant. Everybody wants this in a big system. We actually have to be a little extra careful because we can get kicked off our sources of inventory if we take outages or have bad performance. Must achieve low latency. So this is 150 milliseconds client-side measured latency. So that means like you're on your phone and the app wants to show you an ad. That request goes out. The exchange then pools it and sends it out to all us and our competitors. We bid on it. It comes back and it has to reach the app, and the app's latency is usually around 300 to 500 milliseconds. So from the exchange's perspective, which is our partner, we have to be able to respond from their perspective in 100 to 150 milliseconds. So our server-side latency has to be 30 to 70 milliseconds, and then you've got the internet latency on top of that. So it's pretty tight. And we have to hit that consistently. If we're late, we might as well have just not tried at all. So you have to be pretty careful with that. And we're limited. You can't, like JSON is kind of a computationally expensive protocol to parse at scale. You can't short circuit it with custom binary or thrift or all the different options you have available to you. So we adopted a set of principles as we built it that kind of drove all the decisions that we made as we explored technologies. Read only whenever possible. That's kind of an easy one. You don't want to have to be writing to a database or something while you're processing high frequency, low latency requests. Async writes. Whenever we do have to write to anything, to logs, to Dynamo, to anything, we always just put it in a queue and we have workers spin up and write those out. Horizontally scalable. Our application has 0 state. So everything, every request is completely stateless. And that's really important for being able to just throw servers at problems when you have problems. And then with errors, and this is kind of a scary idea, not trying to prevent errors, this is a system that's spending money. If we're doing hundreds of thousands of requests a second, we can be spending thousands or tens of thousands of dollars a second. And so if you have a bug, say, an off by 1 decimal can be a very expensive bug to have. So we just really focused on detection as opposed to prevention. And that was really important as we grew, because if you try to anticipate everything that goes wrong, you end up over-engineering your solution, or if you just try to focus on what could go wrong and detect it, you save a lot of development cycles, and a lot of the time, that stuff never breaks, or it breaks so infrequently, like 0.0001% of the time, you just don't have to worry about it. So that goes to the next point, which is we encapsulate them. So when errors do happen, we don't want our partners to know about it. If you're using Tomcat out of the box, it'll throw exceptions with a stack trace for you right through to your partner. And so we make sure that we just catch everything up front, and we just have a nice little no message that goes back to the partner at 204. And that way, we look like we're better behaving, even if we're having a meltdown on the inside, say, with some sort of problem. Our partner's like, OK, yeah, no, he's just not buying very much right now, but he's doing well. Internal rate limiting. This goes to very important when you're doing large-scale systems, is that you can have traffic spikes. So think about an app, say some sort of baseball app, during the World Series. Think about the spike in traffic that app gets at that time, and that can flow right through to us. And so we have a rate, basically just a sigpot at the front end that's limits the amount of requests we'll actually process, and kind of like catching errors, we just turn away extra traffic until we can get enough servers online to be able to handle it in an intelligent way. And proven technologies. So ironically, Beanstalk was very new when we chose it at the time, but a lot of the other technologies we chose and we're going to talk about are older technologies. You already heard me say Tomcat. And you have to realize this was a startup. We were 6 or 8 people, I think, at the time. The engineering team was 2. And so if you think about it, choosing Tomcat, the company is not going to fail because you chose Tomcat. If you think about some newer technologies out there, you could potentially have something blow up underneath you, and that could just ruin the company, and it's sort of this a random factor. So some of the technologies we chose are older, but they're proven, and they may not be the most optimal. I'm not sure if you're choosing the optimal platform for a low latency, high frequency system, that Tomcat would come very high on that list. But for a startup, it's a very safe bet, and you can kind of throw money at the problem as you grow until that money is too expensive, and then you can explore other platforms. Okay, so these are quick. Successful system will achieve several goals, and I bet you've all had these same goals for systems you've built before. High request throughput, high success rate, low costs, low maintenance requirements, being able to scale 10 to 100x without major improvements. Those are not new, they're not mind-blowing, but it is important to have them in mind when you're choosing technologies. When you do a load test, you don't load test against traffic today, you load test against 100 times that traffic. Okay, so we're gonna walk through the actual architecture now, and we're gonna start at the 10,000 feet, and we're gonna go right down to the micro technologies we've got. So this is how we organize our Elastic Beanstalk applications. We do it with stages. So each Elastic Beanstalk application for us is a stage. It's production, it's integration, it's sandbox. That's for developers to spin up and test on. And this exists in all our services across our systems so that you've got a full end-to-end environment for each one. We're just talking about the one bidder service here. So if we choose the production box there, we can go down, and inside production, we have what we call clusters. These are Elastic Beanstalk environments. These are just, the bread and butter Elastic Beanstalk. The main difference for us is we've isolated our major partners on their own cluster. And that really helps us with tuning configuration for a partner, identifying problems that are partner specific. Sometimes some of our partners will misbehave in a way others don't, and this really lets us tell when it's our fault or their fault, because as long as we're running the same code across all our clusters, we can isolate problems that are either lower level with how partners are managing their connections, or maybe they're sending us badly formatted requests, but it really makes troubleshooting a lot easier to set it up this way. The bigger clusters are probably in 30 to 50 host range, and we have a couple smaller clusters as well. So diving down, each cluster looks like this. This is pretty much what Beanstalk gives you out of the box in the middle there. Route 53, Beanstalk, auto-scaling group with instances, and then we use 3 data stores on the back end, S3, Elasticache, and DynamoDB. So now we're drilled right in. Don't try to take this all in. We're going to walk through this diagram and let you know why we chose these technologies and how we use them to build our system. So first up here is S3. So S3 for us is really great as a data store for infrequently changing large configuration files. I say large, but they're smaller for us, but it's about 4 gigs of data. And it can be different things, but they're not configuration. They're like targeting parameters or ranks for different apps, or trying to think of good analogies that are general, not specific to advertising, but it's data that every host need. So what we do is we just preload it, so each host comes up, it goes and gets the freshest file. These are refreshed asynchronously in the background on the host, and then we just check the S3 timestamp about once an hour to look for updates, but these don't change that often. But when they do change, they roll out slowly, and it's fine. And yeah, it's about 4 gigs. The next piece we use here is Elasticache, and specifically Memcache. So this is going to go against everything you've read in books. Elasticache is our primary data store. There is no database behind Elasticache. This is done for latency reasons. It's incredibly fast. We know it's transitory, so we detect errors. We detect evictions in Memcache. We invested in learning Memcache and tuned it. And then we have a separate service that exists just to denormalize requests for us and put them for a key value lookup in Memcache. So yes, if we get a restart, it's not the cheapest thing in the world to rebuild. It does cause us problems, and we avoid it, but we do it in a controlled way usually. And it's not a huge deal, because all it does is we slow down for about 20 minutes to half an hour while the cache repopulates. It's incredibly fast. We have not found a data store that can come close to 3 millisecond client-side reads at scale. And we've tested pretty much everything we can get our hands on. And that's been tough to find something that could match that speed. Everything's read-only, so it's just we get a request that comes in, we do our reads. It's always key value. If we do have any joins, which we try to avoid, we do that in software. And you need to tune Memcache. So this solution does require you to invest in understanding how Memcache behaves. Out of the box, if you have weird, I don't want to say weird call patterns, but Memcache can be tuned to optimize space utilization for your call patterns. And so don't just take it for free. And we pre-normalize data. The next piece we do here is cache. So Memcache is our primary data store, and we keep a cache in front of our cache. Each host has their own cache locally. It's a couple gigs, and this exists primarily to solve one problem that we had as we scaled, which is hotkeys. So just kind of like Dynamo, Memcache can also have problems if you get hotkeys that get a disproportionate amount of traffic. With Memcache, you're running on distributed cluster, so each host has its own set of the data, and then if you get a hotkey, you just kill the host that has that data. So we run EH cache on the hosts. It's got short-lived cache times, but the nice thing is that if you have a really hot key in the system, you're completely cushioned on it. And if you don't have a really hot key, it still picks up a fair number of the requests. It lowers the call volume going back to the Memcache servers, which saves you money, which we always like. And the last piece I'm going to talk about is Dynamo. So we use Dynamo for two things. The first use case is reading. So I referred to S3 as storing our 4 GB relatively small sets of data. We have multi-terabyte sets of data that we want available to us online while we're serving requests. This is what we use Dynamo for. And Dynamo has a really nice integration feature with Elastic MapReduce that we already use for a lot of our data processing, which lets you load extremely large sets of data into Dynamo relatively fast and efficiently. So we generate these huge sets of data, and then we load them all into Dynamo. And this is done infrequently. Again, they're infrequently changing data sets. And then you load them with EMR. It's a little bit slower than Memcache. It's probably about 1.5 to 2 times as slow, but its variability is much more reliable than Memcache. And if it weren't for the call volumes and the way Dynamo behaves, we've looked at replacing Memcache with Dynamo. For now, this is working quite well for us. We also use it for writing. So the primary use case is for counters. So it's got a async write increment operation, and since we're advertising, all we do all day is count things. We count the number of impressions, we count the number of clicks, we count anything we can, and we count how much money we've spent. And the nice thing is that this gives us a live counter. It's very fast to update, it's durable, and we can have other systems reading, so at any time we can check and see live how much have we spent. And this is a parallel data set to another track that we keep through our logs to get more details about the spend. This is a very high level, here's what I've spent, but we don't keep details like what I've spent it on. That comes through a separate system. And that leads us to data collection. Mick?
Okay. Good afternoon, everyone. Thanks for coming. Pretty sure I'm the only thing standing between you and beer and freedom, so let's crack on. All right, big data challenge, volume and rates. The first aspect is, what exactly are we going to collect and why? Well, as John said, we generate terabytes of data per day. And we need to figure out what our solid use cases are, what exactly are we trying to report on, and why. So we strategize on what we keep. So some aspects like impressions and clicks and spend, we keep everything. And those things that we just want to use for data analytics, we'll sample. It says 1% on the screen there. Actually, it's down to 0.5% because we realize that's all we really need to be statistically significant. So how does this data actually get into our analytics systems? Well, this is a very high-level diagram, and we're going to drill into each aspect on that diagram as we go along. So the requests come in through Tomcat. We write them out through logs, write the data out through logs. We then use log rotate to rotate those logs on a 5-minute basis. And there's a custom utility, which we'll talk about a little bit more, called TN-S3 Uploader. That's a Ruby gem that we use to upload our data directly to S3 into the right partitions. And then we load directly from S3 into EMR or into Redshift. A couple of things to bear in mind. We have too many dimensions and custom aspects to use something like Kinesis. And also, because we're doing it in a custom manner, we have a bunch of monitoring going on, and we also error out on failed uploads. Right, so how do we actually do the collection? So we have Amazon Elastic Block Store attached to our instances. That's where Tomcat and its configurations live. But we actually set up our local drives in RAID 0 for much faster performance. And these details are in your handout. So I just want to mention the handout you picked up has got a number of code samples in it, but of course you can't copy and paste from the brochure. It's all available at engineering.thinknear.com. If you go there, you will see, these slides are going to be up there once we finish this talk, also links to our open source software. All right, to continue on collection, we write to multiple files. So this improves disk performance, and we make sure we monitor for low disk performance, and again, the example's in the handout. All right, this diagram shows how we actually configure log rotate in our utility. So EB extensions configures the EC2 instance as it gets initialized. And it configures a couple of things. The first one is cron, to actually run log rotate every 5 minutes. And it also configures log rotate. So we have a logrotate.conf file that actually configures each log file that we're writing to. And as part of that configuration, we use that TN S3 uploader to actually upload to the S3 bucket. Once we've done that, we have our data available, but if there are any errors, then we actually mark that EC2 instance as unhealthy, so it gets taken out of rotation. We don't want to have an instance running that we can't collect the logs from. A couple of gotchas to be wary of. First one is Elastic Beanstalk already uses log rotate, so it will run in parallel unless you disable it. And the Amazon S3 push availability is actually extremely good. It's just not 100%, especially when we're sending hundreds of hosts pushing 5 logs every 5 minutes. A couple more. So originally, we were using the host name to prefix the log file. By using the host name, we actually found that they got recycled, especially when you're going up and down 50 to 100% in terms of number of instances every day. So what we do now is we use a custom UUID to actually prefix that host, and that's just using UUID on the host OS. And then we have a monitoring process that tells us when we missed any gaps. Now, since we've used UUID, there's hardly been any errors in that area at all. Again, this is all going to be in our open source software, which you'll see on engineering.thinknear.com. Last thing, cron can crash, so you need to monitor cron. OK, log rotate. So our TNS3 uploader I've mentioned, it's a custom upload, custom gem. It retries uploads on failure, so all that is built in for you. We notify Honeybadger, as that's our current tool, but you can build in your own notification class if you want to use it. Any repeated failures, like I said, causes the EC2 instance to rotate out. And it's open source. OK, scalability challenge. So as you can imagine, network latency is a big area that we want to make sure we resolve if there's any issues there. Well, quite frankly, we use AWS, and it works. So we've not had any issues there whatsoever. There are some aspects we need to be careful of. That includes cross-country endpoints. So if we have an exchange that's on the other side of the country, we're actually deployed in an east availability zone. If we have one on the other side of the country, the latency is just too great for us to integrate with some of those exchanges, so we're going to be deploying to the west. Persistent connections for more efficient reuse when we've got millions of requests going in. And also timeouts from load balancer and Tomcat, which we'll look at in a moment. And when I say in a moment, I mean now. So Elastic Load Balancer's idle timeout generally cleans out connections. So the documentation recommends that we set it to be 1 second lower than the application layer's keep alive timeout, but we actually flipped that. And we flipped that, and we found that we actually got much better overall error rate, which is 200 response code divided by total number of requests. But then we've got these mystery 500 errors that aren't really documented anywhere or even monitored. However, that's the way we still run. So as with all things, you need to test this yourself. Here's a little bit of code. Again, it's going to be in the handout, also in the open source pieces. Let's talk about the ELB configuration, so a connection draining policy. That's configured there, so you can be quite generous with that to gracefully clear out the connections. And then if you want to store all the requests that are coming through the ELB, you can actually configure the access logging policy as well. All right, app server, we talked about this, so I'm going to skip through it. We run on Tomcat, 100% API web-based, nothing to cache. And here's the key pieces, OS tuning, right? So Tomcat typically has 1,000 to 1,400 open files on each host, and those can be jars, pipe processors, and whatever. The two main areas to configure are the limits.conf and the sysctl.conf. So in the limits.conf, the only area we had to look at to resolve the too many open files error was hard no file and soft no file. And for the sysctl.conf, there's a long list, but the two to be most concerned about are the netcore somax.conf, which is basically increased. We increased that kernel queue for accepting requests, especially for bursty traffic. And actually, the TCP fin timeout was default was 60 seconds. We'd have a lot of connections in time wait state using up resources, so we decreased that so we could release those resources quicker. All right, bypassing Apache. EB actually comes with Apache, and originally we didn't really know this was happening, and we're wondering why we're getting slow latency issues. Well, we actually don't need it, so especially because we've talked about not having any cacheable content. So we just turned it off. It becomes another point of contention as well, actually, if you leave it in. So another point to, another area to performance tune and things like that. So we just point the ELB directly towards our Tomcat instance. All right, monitoring, last section. Thresholds. So originally we used CloudWatch, and we need average, min, max, but we need more than that. We need percentiles, okay? But CloudWatch didn't really support percentiles, so we had to actually think about how we're going to do this. So we use threshold counts. So we can figure out what our threshold count is, and then count number that exceed the threshold and kind of work out the percentiles. So we moved to Librato, which made things a little easier. Even though CloudWatch has got great aggregation metrics, Librato allows us to slice and dice the way we want to see the data. So what you're seeing there is a sample graph showing our response rate above 75 milliseconds, and each one of those lines is a different cluster. So we can actually see patterns across the clusters. All right, a couple of learning points. First thing is if you send tens of thousands of metrics per second out to CloudWatch, it doesn't really like it. So we used to get a personal phone call, but now I think we just get throttled. We actually wrote some client-side batch publishing CloudWatch code to actually allow us to do exactly that. Wasn't great, but it got the job done. We haven't open sourced that, and we're thinking about it. So if anyone needs it, then let us know. Right, server-side metrics. Now we're looking at the host OS, Tomcat, things like that. So most of our metrics are collected server-side. We'd love to collect them client-side. However, we need to have a really good relationship with the exchange to be able to do that. So what we do is, to figure out our network latency, we compare the max at the ELB versus server-side latency to get our network and platform latency. And so we set our goals conservatively. So we're very aggressive on the goals we want to hit when it comes to our response time, so that we can have a lot of wiggle room in that 100 millisecond response time the exchanges require. So here are the three libraries we use. We use Librato, we use CodaHell metrics, and we use CollectD to get all our metrics on the server side. We get approximate percentiles, and it's way more economical and no more client-side batching for us. Right, CollectD. So this is very easy to configure. Again, you'll get it when you go to our open source AWS templates project. We configure it via EB extensions, just like we configure everything else. The example config is in the handout, and again, like I said, go to the open source project, you'll see it. And the final aspect is Tomcat. So just an example, we collect our Tomcat metrics via the CollectD plugin, and here's just an example for mbeans that we export. So I hope that's given you a flavor of what we've done to actually serve these huge number of requests on Beanstalk. We'd love your feedback on what we've open sourced. Please come along and have a look at the engineering.thinknear.com. Do contribute to the issues if you find anything with the libraries open sourced, and feel free to ask us any questions.